I'm a math PhD. This is kind of more or less a math talk. We kind of planned it should be like a general talk, a general audience talk. So I hope it's not, it's either too easy or too hard or wrong on all counts and in the middle. It's a story about network inference through information flow. I'm going to spend a lot of this time telling what I mean by information flow in terms of information theory sense. And my shtick in causation entropy is going to be about this phrase direct information flow, as opposed to general information flow. Erik Bollt. So we're up here at Clarkson University, right near Canada, 15 miles from Canada, rural upstate New York. Looks like that in the autumn. I'm going to get back to autumn pretty soon. I'm director of Clarkson Center for Complex Systems Science. So that's this. This is what it looks like in a little town. Here's my house. And I'm working lately with Dr. Paul Laurenti at Wake Forest University. And guess who that is? Yep, you might recognize it's me. So I had the pleasure to, as an introductory to a new NIH grant, we have Introduction to the Equipment. He's an MD, PhD radiologist, and he was introducing me to the equipment we're going to be using for doing network inference in fMRI images. And so that's my head. That's a bold, this is a bold signal from my head, and this is eventually a network that we interpret of me doing a certain task. I keep walking over here because I'm not used to having one of these. So what this talk is about generally, it's not about that. I call it causation entropy, but a lot of people would argue it isn't really causation, it's really information flow. So causation is about what made stuff happen. So does fossil fuels cause climate change? Does smoking cause cancer? Why did I get fat? And things like this, the chicken and egg story. So causation has a beautiful and long philosophy behind it, all the way back to Aristotle and Hume and Russell. And I like very much this version in Do Calculus by Halpern and Pearl. And I just realized yesterday that I'd like to meet Pearl. He's here. I've never met him. You're not here, are you? I don't even know what you look like. So anyway, that's fantastic. This is an alternate story for causation, and it has a strong history of why it also could be causation. It's information flow, and it's about reduction of variance when you make forecasts of some of the bits x based on just looking at x, or based on also looking at other variables y. And so that goes by the phrase Granger Wiener causality. So Wiener from like Wiener processes described that first, and then Granger later, an economist, made a formalism to work with that in terms of regression, and he won a Nobel Prize for that in economics. So it's a non-intervention philosophy, where this is an intervention philosophy. You set up experiments and you poke the system. So this is called YG causes X, and then the process. So this is Wiener. Oh, this is Wiener, Clive Wiener. And so what I just said, does X allow you to forecast the X on its own, or should I also be taking in variables Y? So this is like a time series from X. Here's a time series from process Y. And I'd like to forecast Y, so this is XG causes Y. If I want to forecast Y, do I just look at its own past, or would I do better by also looking at the past in X? And the rest is in the details of how you might actually decide that, but that's a basic question. So there's a number of different ways of getting after it, and Granger got after this in terms of autoregressive models, linear models, and later ARMA models, and so forth. And then there's a information theoretic way of getting after the same thing. So the general story of network inference, sometimes called network tomography, is I measure time series at lots of different states or a parcellation of a network, maybe a brain, maybe the bold signal. And based on looking at just the time series, I'd like to figure out what's influencing what. And not just that, I want to emphasize again, one word in my title, direct. Because I argue, in my questions yesterday, I was arguing that the direct gives you a different kind of an answer. You need a condition on intermediaries. Does X cause Y and Y cause Z? Or does X cause Z directly, or only through Y? That's the kind of question you'd like to distinguish if you actually want to pick up the actual network, because otherwise you may pick up an all-to-all network when it's really everything is coming through chains. That's my punchline, so I just gave away most of the talk. So applications from gene expression networks, social networks, food webs, and we're here for neurons. Identify the causal interactions. And then I may get to a point where I'll show you a little bit about a climate application. So a long time ago, before I actually made any headway, and I started in dynamical systems as a math student, I learned about symbol dynamics. It's kind of one of my very favorite mathy topics in dynamical systems. And symbol dynamics is kind of nicely realized or described in terms of a toy. So this is kind of me in my instruction mode. Can I find a little starter button? Yeah. So there's a toy on my desk. So it's a pendulum, it moves around. And every time it reaches a local maxima in the angle, I'll just say, what color is it over? Is it over one of these colors? So as it's over the colors, maybe it will be over the orange. And then later on, it's over the green, and then maybe the orange. So I might go orange, orange, green, orange, orange, green, as I read off in the time series. So this is one of the angles. This is the other angle, because it's a two-degree pendulum. And then the derivatives, that makes the phase space. But I'm just going to read off the angles in here. Now we can argue if that's the real symbol dynamics or just a symbol dynamics, and that's a long, beautiful discussion that I played in a long time in the past. But anyway, it makes a perfectly good symbol dynamics, and you can agree that it's kind of like an information stream. In fact, if I just divide it left and right like that, I would have streams of zeros and ones. And we know that zeros and ones can encode all kinds of things because of our experience in computers. So as time goes on, this dynamical system is expressing information. And all that information is encoded, you could argue, in the initial condition. So a dynamical system expresses information. And these are some beautiful textbooks on that. Dynamical Systems and Symbol Dynamics by Robinson. I like this book very much by Lyndon Marcus. And that one by Bruce Kitchens. So this is the question that got me started in the whole topic, is what if I have two dynamical systems? Same one, in this case. Two of these guys' pendulums. So if I run them, can I run them? Yes. Go. Nope. Go. See, they're just both doing their thing. And on the guy on the left, I'll read off symbols, green, green, orange, yellow, green, green. And this one, I'll read off symbols, blue, yellow, green, orange. Except the way they work is this pendulum has a little magnet on the tip and an oscillating magnetic field on the bottom to keep it running. Same with that guy. And when they're far apart from each other, they essentially have no influence on each other. But when I bring them closer, the pendulums that have little magnets on them, they attract each other. So they're obviously influencing each other. So I could argue that this one was going to say green, green, blue, but it might say green, green, yellow because of the tug on that one. So that one does a little bit different information because this one is kind of in a way talking to it and is listening. And vice versa, that guy might be talking to this one and it's listening. So what does that mean? It's talking to it and it's listening. It's trading information. It's affecting its state. So somehow there's an information stream running between them. And the information stream is running on, it's being carried on the magnetic field. So it's kind of a second story for the usual story of physics. In nature, forces change states. They change energy states. But the second story is I have states that can be coded by symbolic streams, and the energy carries information between them. So to make that a bit more relevant, I'm going to give a quick review of just some of the words in information theory. So why I think every dynamical systems person, anybody, should have some information theory under their belt. Information theory in dynamical systems is very natural. So my favorite book in information theory is this one by Thomas and Cover. It's fantastic. It's like a Bible of information theory. But the discussion I'll give is just a little bit in a chapter I have in an old book of mine about, I have a chapter about that title, why every dynamical systems person should have some information theory. So my understanding of information theory is you can think of it as a coding concept. So you assign short words for likely or frequent source symbols And then you have to penalize yourself by giving long words for the unlikely guys. So I'll give you, so it's kind of like whenever I'm surprised, maybe there's a long symbol. So let me tell you what I mean by that. So here's a word, chaos. And I can code it in ASCII format, the American standard for coding something, like this. So this 7-bit stream is the big C. This 7-bit stream is the H, the A, the O, the S, right? There's a whole code. And what that ASCII does is for every letter on your keyboard, it gives a 7-bit letter, a 7-bit stream of zeros and ones. So when I say chaos, it's C-H-A-O-S, that's 5. 5 times 7 is 35, so it's 35 bits. And everything will just go at that 7 bits per letter rate as if I stream across text and I just see how I code it. But can I do better? And I can by entropy coding, and actually it's how you would understand entropy coding. So here's a game you can play. So I just said, I'm going to take a simpler word just to make the game easier. So I'm going to take this word, CH, CHO, blah, 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 like that word up there in blue. And if I did an ASCII, it would be 20 times 7, so 140 bits as I read across it. And you can pretend that's colors like yellow, blue, green, green, blue from my pendulum instead. Here's a very simple probability model for what I see. So you might do better with better probability models, and that's a whole game of statistical modeling. But I'm just going to count out how many times relatively the C occurs, and I just count out it occurs 40% of the time. And the H occurs 35% of the time, the O occurs 20% of the time, and the P occurs 5% of the time. Good, so now what can I do with that? So here's a particular coding. It's the Huffman code, actually. Since C is the most likely, I'm going to say, good, 0. I'm going to say the bit 0. Whenever I say 0, it will refer to that most likely guy, the C. And now if I want to say H, I need to say it's not a 0. So that's what the 1 is for. And then I'm going to say, good, that was the most likely next guy, so I'm going to give it the 0. And then, if I want to say the next thing that could occur, I have to say it's not a C, it's not an H, and I'm going to give it the next most likely guy, so it's the 0. And then the leftovers go to the P. And that's also a pretty good code, but we need a probability model to use it. And both the transmitter and the receiver can pack and decompress with this. That's kind of an important aspect about coding. It has to be invertible to be a code. Anyway, using that guy, this word, instead of 7 bits, codes up in 37 bits using that code, or 1.85 bits per letter. So a big compression. And that's kind of the heart of what Shannon information is about. So this is my understanding of Shannon information. Is this basically this average? So probability the ith letter occurs in a message. So the weighted average would be 40% of the time I get away with 1 bit, 35% of the way I use 2 bits, 20% of the time I use 3 bits, and 5% of the time I also use 3 bits, for an average of 1.85 bits per letter. And that's basically what the Shannon entropy is, sort of. So a D-ary code, in this case it's 4. For random x with a probability distribution rho of x is given by this weighted sum. So I can get away with, this is the compression rate I get that corresponded to those shortened codes. And it takes a bit to prove that this is the right thing, but it's the idea of what we did. Log of p occurred with probability p. And that's the Shannon entropy, this mean with a negative symbol. And the word length is that thing, which is the negative log p of x. So that's the idea of it. It's not a proof of it. And that's entropy. So for many random variables, if I have several random variables, like 2 coupled pendulums instead of 1, then I would have 2 of these guys. I can describe different kinds of entropies associated with it. I can have an entropy for the complete process of the outcome space for the first guy and the second guy. It'd be the whole thing. I can have an entropy for one of them, like that's pendulum 1, that's pendulum 2, I have an entropy for that guy. And I can also do conditional entropies. This guy conditioned on that did not happen, this guy conditioned on that did not happen, or the joint bit, which is the intersection set. So then there's an interpretation for each of those. So the joint entropy is just p log p for the joint probability distributions. That's the sometimes called the total entropy. The conditional entropy is this kind of green stuff with the purple cut out. So I can say it's the conditional entropy of x1 given x2, which is that bit, plus the entropy of the whole bit for the other guy is this joint entropy. And I can take this, subtract that off, and I can take that as the definition of entropy of x1 given x2. So this is a theorem one can prove that the joint entropy of x1 given x2 is 0 if and only if x is a deterministic function of x2. So there's no surprise when I see x1. I see x2 because it's a function of x1. x1 given x2 is h of x1 if and only if x1 and x2 are independent. That's kind of a very interesting statement. So it's about the remaining entropy. So x1 given x2 is a remaining entropy after I already told you what x2 is doing. So here's the bits I need for the discussion of information flow. So mutual information is discussed a lot as kind of a comparison between two random variables. It's defined by that formula, which I prefer written in this format. The log splits up as a difference, and it turns out it's the entropy of x1 minus the entropy of x1 given x2. So it's a symmetric quantity, and it's the amount of information that knowing either one tells you about the other. And then finally, this is the thing I really need, which is called the Kullback-Leibler divergence. It kind of serves like a distance-like function between two probability distributions, P1 and P2, in information theoretic terms, because it comes in units of entropy, which means entropy is always in units of like bits per second, or bits per read symbol, or bits per, if I'm reading symbols, like if I have a reading rate scanning across text, the rate at which I read symbols. It's always bits per a time-like thing. So it's defined as this quantity. Is that a fire alarm? Mm-hmm. Okay, p log p1, p2. This expression, and I prefer to split up the log as a difference. So p1 log p1 minus p1 log p2. That helps me interpret it. Because p1 log p1, that's the entropy of p1, missing the minus sign. And P1 log P2, that's kind of like, think in terms of the coding I just did. Log P2 would be how I would code using the Huffman code, a process P2, and then I would use it in a process P1. So this is what would happen if I would use the Huffman code for the wrong model, the wrong probability distribution for something that's already occurring P1. And this would be the right compression, and this would be the wrong compression using the wrong model. So it's kind of like an efficiency. So this sometimes is called cross entropy. So it's the cross entropy difference from the true entropy. You can check just by properties of logs it's not symmetric, which is one of the reasons it's not actually like a norm between probability distributions, but we use it a lot like a norm. And this is a nice expression for mutual information. It's the Kullback-Leibler divergence between x1 and x2 versus p of x1, p of x2, which is what that would equal if these were independent random variables. So it's like a deviation from independence. Actually, I'm going to jump to this and then jump back. No, I'm going to do it in this order. Okay, I'm going to stick with the order. I had changed my mind. This is actually the first project way back in the day when I was fresh out of grad school. Is the date here yet? 1997, fresh out of grad school. When I did something with entropy in dynamical systems, I really got the hang. It's a very fundamental quantity if you want to do dynamical systems. This is a flow x, y, z from the Lorentz equations, which are so famous. This is the Lorentz butterfly. This is a time series of time versus z of the same. And I've symbolized it by a particular trick. So I'm reading off zeros and ones as the oscillation goes, based on a trick that says every time this time series hits a local maxima, I'll tell you whether you're high or low. And the high or low is based on whether I'm on this lobe or this lobe. And there's a map that corresponds to it, which is a successive maxima map. We can just say whenever I'm on this side and I reach my high point, call it 0. And every time I'm on this side, I'm at a high point, call it a 1. So as this guy goes, it's just saying zeros and ones. And in the mid-90s, a lot of us were doing control of chaos, and you can control trajectories to do different things. And so this particular trajectory, I did some stuff behind the scenes, and it says the word chaos. So that particular flow is saying chaos in the Lorentz equations, chaos. And that was a PRL. So there's a story about how fast I can actually do it. Turns out the dynamical system, this differential equation, can't say anything. It has a restriction. It just never turns out that you'll see two zeros in a row. It just doesn't do it. And that's a reduced entropy. So it doesn't make the maximal entropy, which would turn out to be log 2. It does something a little less. With no two zeros in a row, it ends up having an entropy of golden mean, log of golden mean, which is kind of a fun result. It's called the golden shift, no two zeros in a row. And it's actually a little less than that, but so that's an upper bound. So no two zeros in a row, both transmitter and receiver would have to know that. So every time I see 1 0, you're forced to put in a 1, no matter what. There's no information bearing capacity to that. So you say a 1, that's like a dummy bit. It's like lost time. And then you can transmit whatever you did want to say. So both receiver and transmitter have to know that. And they have to strip off the 1s. And after that, then you can read off the ASCII. So that inefficiency is kind of a reduced entropy of the process. And you can think of any dynamical system as an initial condition has information, like I want to write down that state in high precision, store it on my computer, like 0.367425. I can store that in my computer as streams of zeros and ones. And then how many I need would be like the entropy of that, how often those occur as the system evolves, by I just said. You take the initial condition, you feed it into the differential equation, Lorentz, and it makes new states. So you can think of a probability of the new state conditioned on the old state, and then it makes output states. And it would also have probabilities. And there's a whole kind of mathematics for how to evolve probability, and you can measure those with entropy. So the transfer operator for Briones-Perron would push that forward, and you can measure entropies. So I can think of this process, the dynamical system itself, as allowing you to say, how does the future and past relate? And I can say, what's the most I can push through? So that would be the mutual information from the future and the past, what's the most I can push through? And there's a thing for that in information theory called channel capacity. So I can ask, what's the channel capacity of the process? Is the maximum over all such probability distributions. So that's a way of thinking of channel capacity. So that was kind of the story of that PRL. But then I was itching for something that would describe that process, but someone else did a fantastic job of it. And I was excited to learn about this paper when it first came out, 2000, by Thomas Schreiber. He knocked it out of the park. So it's called information transfer, and he developed something called transfer entropy. So a lot of people use this thing called transfer entropy. And a lot of people use it incorrectly, and I'll show you that in a minute, but that wasn't Thomas Schreiber's fault. So let me first show you what it is. So transfer entropy is meant to be saying how much information is flowing from process X to process Y. I'm sorry, I said that backwards, from process Y to process X. And it answers a question to tell me what the transfer entropy is. It says there's two different versions of reality, and I'm going to decide which one's right. So one is maybe X, the future of X depends just on X. It's a function just of X is past. Or maybe the future of X depends on X and Y past. Which one of those is true? If it's this one, it means X needed information from Y, which means Y is sending information to X. So how do I decide which of these two is the right story? I'm going to ask them in probabilistic terms, because entropy is essentially a probabilistic story. So is probability of xn plus 1 conditional on xn equal to xn plus 1 given xn and yn? If that's true, I don't really need yn. So this, I should put a question mark over this equal statement. So how do you say, is this the same as that? In information theoretic terms, you just grab these two things and put them into a Kullback-Leibler divergence. And if you get 0, then you say, in probability, they're the same. So the Kullback-Leibler divergence measuring these things, two things, is defined as the transfer entropy from y to x. And that's the heart of what's in this paper. And it's been used a lot by many, many people in applications ever since then. Even today, you'll find papers published in current issues of various journals. And vice versa, I can ask this question in reverse with y's and then xy. And I get the transfer entropy the other way. And since Kullback-Leibler divergence is not symmetric, neither is the transfer entropy, which is nice because you might have one is coupling one way but not the other way. That's quite allowed. So that's very natural. So people use it in all kinds of settings, stock market, genomics, bioinformatics, brains. But it misses something about direct versus indirect, which is where my story is. So now I've got enough background to start my story. But anyway, around 2012, I had some paper, a solo paper just about using that for synchronization, and this is an example of just two simple maps that are tent maps. Two tent maps that are coupled diffusively with an x and a y. And for a low amount of the coupling, they synchronize. For a little higher coupling, they kind of almost synchronize. Synchronize means the two different initial conditions, the error goes to 0 as time goes on. And here the error doesn't grow, but it doesn't shrink either. It kind of hangs out at some kind of modest small number. And if I make it even higher, they don't synchronize at all. And so in a process like that, I can say, well, tell me about the transfer entropy as I vary these parameters. And they can make a transfer entropy plot, and there's kind of in the delta and epsilon, there's a kind of a region where they synchronize strongly, and then not so much, and then not at all. So here's a version of it where I'm turning up one of the couplings. And for small coupling, there's a lot of transfer entropy because one's talking to the other one a lot, but it's not really listening a lot. At some point, they synchronize at a coupling strength. Then once they synchronize, the transfer entropy is almost 0 because it's kind of like one's whispering to the other one. But then the mutual information becomes high. So the mutual information and the transfer entropy kind of serve like opposite roles. I included that for that transfer entropy, so information flow versus mutual information story. Now here's the direct versus indirect story, and where causation entropy, my thing that measures direct versus indirect, comes in. So causation entropy is a kind of a generalization of transfer entropy for building networks. So here's a very simple network. Z connects to Y, connects to Z, and I run some kind of stochastic process or some kind of map on that graph, on kind of several other graphs. You can make all possible 3x3 systems, but here's just one. And as I turn up a coupling, I'm going to measure the transfer entropy of Y to X. So the transfer entropy of Y to X, as I turn up the coupling, it's rising. That's kind of what you would expect. And the transfer entropy of Z to X, that's this one, it's also rising. And so if I'm using transfer entropy to decide the network, looking at this picture, I would think there's a connection from Z to X. And that's not what I want. Well, I probably don't want that. If I want to build the network underlying the process of coupling is the process, then I don't want that because I would draw that connection. And sure enough, well, that's because transfer entropy is designed to answer the question, does Z, knowing Z, help me forecast X? And it does. So it's correctly giving me that red curve. But I should be asking a different question if I want to find the network. What I should be doing is saying, good, since Y is influencing X strongly, the strongest, I say, good, let me accept that as truth. And let me make this connection here. And any other question I ask, I should say, given I've already accepted that. So that's a conditioning statement. Given Y is speaking to X, so given this curve, how much remaining entropy is there? And I have the tools and all those and information there in terms to do that in terms of conditional entropies. So given this curve, the remaining entropy, Z2x, is essentially 0. So that's causation entropy, and I'll show you the formula for it in a second, but that's basically the question underlying it. So that's what the symbol Z2x is. So with that, you can recover networks. I'll say a bit more on it. But here's a more mathematical definition of causation entropy, our object. So this was in a paper of ours in 2014, and then we filled up the details in 2015. I'll cite that in a minute. You write like this: the causation entropy from nodes X to nodes P conditioned on states I've already accepted S. So these can be lots of states in a network. Is this kind of, it's essentially a Kullback-Leibler divergence. So it's P's given S's minus P's given S's and Q's. And that does the thing I spoke out in the pictures. And this, in terms of X, Y, Z, I can speak in terms of a Venn diagram for the process. So this part would be the X process. So this would be the autonomous part. This is the Y process. This is the Z process. This overlap between the X and the Y is where the transfer entropy Y to X exists. This bit is where the transfer entropy Z to X exists. And this little bit, the triple intersection, is where causation entropy from Z to X given X and Y exists. And so whether this is a positive quantity or not is just telling me whether there's any remaining intersection that was not already accounted with the double intersections, if there's any remaining triple intersection. So you're asking if this red bit is an empty set or not an empty set, and you're measuring how much, that probability in entropy terms. Good. So that's what causation entropy is. Causation entropy is just a measure. It's just a kind of entropy. Under assumptions and how you use it, you can use it to make an algorithm we call optimal causation entropy, and that was what in this old paper of ours from 2015 in SIAM Journal Dynamical Systems. And the assumptions are, if I have a process that generates a stochastic process X, and in time it's temporally Markov, which means I'm only influenced by my graph neighbors. It's, I said that wrong. That's spatially Markov. Only influenced by my graph neighbors. It's temporally Markov, which is the usual thing. I'm only influenced by past. And there's an extra condition you need, which is called identifiability, which is this expression can be thought of as links don't cancel each other out. So if you had a process that was always saying opposite, then you couldn't identify it. So I think of like noise canceling headset. So if it's always feeding an anti-signal, then you wouldn't be able to hear the signal. Under that, you can recover the network. We had a theorem in that story goes. And the theorem says that this process recovers it, which is you should identify the maximum set, maximum information between groups maximized over neighbors, argmin over the set of neighbors, the size of the set of the neighbors. So it's a mathematical way of saying the thing I did, which was find the biggest effect, condition it out, and then look successively for the next biggest effects, is encoded in this statement. If you do this, it's almost the optimal causation entropy principle. So that's the functional. And in practice, we do it by greedy search, which is you go through and look for the minimal set, and then you have to give other guys a condition, a kind of array Peshage round, where they have a chance to come back as possible influences because they might be long-range influences. And the greedy search, it tends to do quite well, and it scales nicely with network size. Okay, so I showed you this. I'm going to show you something about the direct and indirect in a second, but let me just show you this. This is a process where we can do everything in closed form with what I just showed you. So this is a linear stochastic process. You can think of it like an auto. Yes?
Sorry, could you go back to the
sure.
slides? Your Cmax, is that depending on I, on little I? I mean, there's a little I on the right-hand side that doesn't seem to be.
Right, so I run this guy, so that's I. argmin of this guy. So for any given value, take the smallest k you can. So this is the count on the number of neighbors.
So that would depend on I. That would depend on I?
Yeah.
Okay, so...
It's kind of, if you're thinking in terms of like standard continuous like optimization, that would be an utter mess to work with. But the thing I spoke out, the greedy search, it is reasonable to do because it just says, try to maximize this, but only add in one guy at a time. That's the greedy search, and try to...
Maybe it's a good question again.
But actually doing that for direct, it would be a mess. So an approximate solution is useful. Okay, so a linear stochastic process. So this just is x updates by a matrix plus noise. It's nice because that has a closed form solution for a normal distribution on x. So normal on that guy. And this is the solution. So it's a series solution in matrices A. And quantities that have to do with the covariance. So anyway, you can solve it in closed time form. That would be the phi matrix. That's from time series analysis literature. It also shows up in linear control theory. So with that, in the Gaussian version of the noise, you can compute the entropy of the process. That this is a standard computation. The entropy of the process has to do with the variances of the normal distribution. If it's normally distributed, that would be the variance matrix. And something having to do with size. But anyway, it's possible to compute the transfer entropy in closed form between any pairs. It works out to be this thing, which has to do with elements from diagonal and off diagonal between the different processes. So it's kind of an ugly form. It took me a while to describe where it came from and even how to read it. So let me just say I've got the transfer entropy in closed form for that guy. And I'll show you a picture of what it produces. And I'm going to contrast it to, I can do the same for causation entropy. So anyway, for a linear chain, the transfer entropy actually gives the correct answer. It does perfect. For a tree, it does a terrible job. So for a tree, you can show that the causation entropy, which would give all these arrows, including the red arrows, so the causation entropy, the transfer entropy on this guy would think that's its parent, but would also think that's its parent because the parent has a common parent. So it picks up all the indirect effects, which is kind of the thing you could have guessed. You can just show it in closed form. And you can show, this ends up being the causation entropy as I described it, and it's based on determinants of submatrices of the P's and the Q's and the S's from I showed you before. Anyway, applying the formula, you can show that it picks up the exactly correct network. So we applied this to a number of scenarios. I'm going slow, so I'm going to skip one or two of the scenarios. Not just as applications for a little while. Does a movie run? No. Does this movie run? Yes. So this was just dots moving around, just like these dots, except these dots have lines. So these are insects. It's these insects, but in a lab. These are called... That's a Russian guy. I don't speak Russian. This is in the Arctic, where they have lots of these insects, and they're big. So a big bunch of them. It's these insects, Chromarius riparius, that are in a big box and are shot with lasers. And then, so it's a PIV method, it's called. And then the lasers can identify their position. And based on that, if you apply causation entropy, our problem was to decide which insect is influencing which other one. Are they following each other? Is there a leader-follower problem going on? And that was the network that comes. It's a time-varying network for the insects. So we're getting a little closer to the application of brain. But anyway, it turned out for this story, for these insects, that the insects weren't necessarily being influenced by their neighbor insects, but sometimes by ones on the other side of the box. And if you'd actually eyeball it, you would see sometimes that you have a big bunch of insects in like a swarm, and sometimes guys on opposite ends would start doing this. And I was thinking that like tango, like they're dancing with the guy across the street, the guy across the room. So we made a graph of the near neighbor intersections versus the true intersection. There was a distinct difference. So we've applied it to all kinds of different scenarios. We had a DARPA grant for a while that was applying the causation entropy for intelligence data from different kind of textual data from a fake theater that had to do with things like crime, government activity, violence, all these kinds of different things, and we're seeing which elements influence which other bits. So we had these like long time series, and eventually we're going to try to build a network. And underlying this story, there's a whole kind of mess of computation I'm just going to give you a hint of that is necessary to do any of this, which is estimation. So I said, good, take the probabilities and compute the entropies, which is actually quite a trick because you need a probability model of some kind to estimate those entropies. So if you just say, okay, everything's Gaussian, and I try to estimate the parameters of the Gaussian, and it's kind of rather straightforward, but Gaussian might not be the right model. So that's what we were doing initially when we were actually doing the estimations I was showing you. And it does kind of okay, except for problems that are not Gaussian at all. This ended up being very Poisson-like. And Poisson distribution-like processes, they tend to be, they're called time point processes, and they tend to be very spiky. So nothing happens, you got lots of data where nothing's happening, and then suddenly there's an event. So we've gone through kind of, over the years, a number of different estimators, and we built our own estimators, or sometimes they existed, for computing entropies in terms of parametric distributions of various different kinds. Here's our multivariate Poisson estimator, and I'm only flashing it here to show it's an ugly formula, but with parameters you can estimate, which are the rates. And you can go directly from the rates to the entropies if you're good with the kind of like moment generating functions that go along with the whole kind of probability field. So that's one game one needs to do if you want to do parametric estimation for the entropies. We've done Laplace, we've done normal already existed, we've done this, we've done a Hawkes process lately, which is very useful for certain kinds of processes, which are kind of like Poisson processes, but with a bit of a memory. They're self-exciting. So parametric distributions are great in that they tend to converge more quickly, and if you're justified to use a particular parametric distribution because the process is a bit like, the experiment is a bit like the parametric distribution you're using, you'll probably get reasonable results. It tends to converge faster, meaning less data gives you pretty good answers. But there's also non-parametric estimators, and this is my favorite non-parametric estimator. I'm going to describe it in a second. But non-parametric estimators in high dimensions tend to be very data hungry, and so not so fast converging in terms of the amount of data you need for the amount of precision you might get. So you would rather avoid a non-parametric estimator if you can, get away with a parametric estimator, but sometimes you just might have no idea what the right parametric distribution is, and you have to go this way. So there's a penalty. The good thing is it's kind of black box. So this is my favorite one. It's from the category of estimators called nearest neighbor estimators. This particular one is by Peter Grassberger and group. He has a way of going from near neighbors directly to mutual information. And I showed you a formula earlier where mutual informations actually are directly linked in some sense to Kullback-Leibler divergences. So you can manipulate this kind of estimator to estimate transfer entropies and causation entropies and so forth. So anyway, the idea of this thing is, I'll show you in a second, but it's based on, you take a point, and I say, show me its k near neighbors, and count them. So actually, instead of that, I'm going to do a range search. It's like a near neighbor estimator. A range search says, show me all the near neighbors within epsilon, and count them. How many are there? So maybe 5, maybe 6. And based on that number, I can go directly to an entropy based on understanding how big a ball is supposed to be in a d-dimensional space. So it kind of flips the problem of estimating entropies. So instead of looking at the space, and I say, divide the space up into little boxes, count how many guys are in there, which would be like making histograms, and then from that, my probability model would be histograms, and then take p log p of those histograms. That's an inefficient way to go because often you have large bits of space with no data in it. It instead says, look at the data and only compute probabilities where I actually already have data. So I say, how likely was that guy? Well, if it's likely, then near neighbors will be very close. And if it's not so likely, the near neighbors will be rather far away. And with that germ of an idea, and the idea of how big balls are supposed to be in terms of in high dimensional space, and you use the gamma function, you get a nice formula. So all that stuff goes on in the background. I'm actually very close to finish here. So we've been applying this to fMRI data. There's not me, there's someone else. So the idea is you take an fMRI bold signal. This machine, each machine's different. The fMRI machine, the MRI machine gives 20,000 voxels, which is the resolution. It's like a pixel size. So it's the resolution of the machine. And how much resolution it can get has to do with the magnetic field, the strength of the magnetic field. And we can make I don't know if you've ever seen an MRI machine, but they're already very big magnets. And you can make very, very big magnets, but not apply them to humans. So I'm trying to remember the unit. I think it's 3 Tesla was the machine that they stuck my head in, but I might be missing an order of magnitude, but I think it was 3 Tesla. And Paul tells me they go up to roughly 7.5 Tesla applying to humans. And after that, we can make such a thing, but not put a person in it. And already in that machine, I can tell you my face was going through like waves of muscle contractions after a while, which was kind of uncomfortable, but I thought it was so nifty, it didn't bother me. But I was then thinking about what it'd be like in 7.5 machine, and then it must be a disaster if you put it too high field. Anyway, that's where the resolution comes from. This is 20,000 voxels. There's a bunch of pre-processing steps that happens before it, which has to do with registering the data. My head might not be in a standard position or rotation, and then also scaling so that the image is steady and in the right place. And then there's more software that then divides it up into anatomical regions, which is a reduction of dimension from the 20,000 to about 250. And that's what the colors are. They're the anatomical regions that are identified. And I would assume a brain surgeon would know by memory each of those anatomical regions. They'd be the same for each, like a pinky and so forth. I have those in my head. And then for each of those, you're essentially we are picking up the causation entropy between the relevant bits. Okay, now this is going to be the closing bit of my story in a second. That's my head, I already showed it to you. So we don't have this discussion yet for fMRI data. This is for a different kind of a process, which is called DTI, diffusion tensor imaging. So one second, I'll tell you why we use that for our prior study. So we're in process of doing this for multiples, so a group study across addiction patients and a large study that was previously done with our causation entropy principle and contrasting it to what's standard practice now. So standard practice now is essentially to build networks by correlation method, which Heather, are you here? Discussed yesterday. She's not here, and she's also at Wake Forest University. But anyway, that's across the industry. I believe that's the standard process is correlation method. And I claim that a correlation method directly applied, you heard me say it yesterday in questions, would make the error of not being able to distinguish from direct versus indirect. And then also, a correlation method is going to be symmetric, so it will not be able to pick up directionality. So you need some kind of measure to pick up those things. One could do it in the world of correlations, but I'm doing it in the world of entropies. So I want to distinguish direct versus indirect, and I want to be able to pick up directionality. So we built a data set which we called pseudo-synthetic, because we have a real network that came from diffusion tensor imaging, which is kind of like a dye process. That builds by direct observation a network, and on that network we ran a synthetic data set. So we built a data set from running Kuramoto oscillators, which are basically phase oscillators in terms of coupling between pairs sinusoidally. So this is a data set for that process running on a real network. And here it is for a rather lower coupling, a higher coupling where things seem to start to synchronize, and a very much higher coupling where there's a great deal of synchrony, or at least chimera, so synchrony between groups. So there's a kind of a story between when chimeras show up and why they would show up, and symmetry networks that allow it to show up. And that's a beautiful story. But anyway, I'm just going to say, here's my data sets. For these, actually, we've done it multiple times, but I'm only showing you one. Here's a network, a recovered network. And here it is presented as an adjacency matrix. So there's an adjacency matrix from a DTI network from data like that. Good. So now I should be a benchmark, and this is why we're doing this process, and that was what was in this paper of ours, 2021, with Paul and my group. And my other students. So Ab Almoni, by the way, who I say, yeah, he just got a tenure track job. He's now at Embry-Riddle. So we can contrast this in terms of a ROC curve, which is radio operator curve, which measures true positive versus false positives as you're varying a parameter, which is a threshold parameter, for different ways one might pick up the network, counting out how many of these are true positives and how many of these are false positives. And this curve is the correlation network. And I showed you why I think it's picking up lots of false positives. And anyway, it does okay, but not fantastic. There's another curve on here, which is a lasso curve. Lasso is essentially a linear model plus something that emphasizes sparsity. So it's L1 regularized in terms of the number of coefficients. It's saying, show me the network that fits the data and also has as few non-zero entries in the result as possible. And there's a parameter in the lasso process, which is a regularization parameter. And you have a difficulty, you have to have a way of deciding where I should put that parameter, because as I tune that, I pick up more or less value. So it's kind of a sloppy parameter that is always kind of a nuisance to pick up. There's a lot of ways to pick it up. But even before you pick it up, it gives you false positives and false negatives along this curve. And there's some best position on here. It turns out to be right over here, but I'd only know that if I actually knew the answer. So I can't say I'm going to pick that one up. So there's different criterion for deciding how to pick it up. One has to do with cross-validation, one has to do with BIC, and the BIC does best. BIC stands for Bayesian Information Criterion. So that's the best you would likely to pick up. And the green curve, so actually Lasso does very well. And a lot of people use it. The green curve is our curve, which is the, we call entropic regression, which is a version of causation entropy, but between data and basis functions, picking up basis functions that pick up oscillating things. We have a whole story on entropic regression as well, which is another way of picking up sparsity problems. That's for discussion for another day. But for the discussion here, you can pick up the best value kind of automatically, because it was the oCSE that I had showed you previously, which says that mini-max thing I was doing. And so without worrying about that thresholding, you can pick up the whole range, but we would pick up the star, which is the closest to true. And of course, it's not perfect, but it's pretty good with a finite data set. So I'm going to say that's about the end. I'm just going to wave at this one, but not look at it. Anyway, I've kind of been in the business of applying to all kinds of other settings, and there's a lot of people do it. This was one of these papers for, it was for climate, and it had about 20 authors, including me, were discussing a whole range of causation methods for deciding things about weather. Does C affect the weather and the climate downstream, and so forth, a lot of different settings. So that's just kind of a cartoon as far as we're concerned. Here's the long title. And the different kinds of methods were Granger causality, transfer entropy, causation entropy, CCM, which is cross-correlation method, which is, I think, poorly named, but it's a good method, by Sugihara at San Diego, that says make a forecast and make it twice. Actually make the forecast by whatever is your favorite method. And then pick the one that's best, but maybe do it multiple times so you can build a statistic out of it. So I'm not a fan of that because that's what entropy is already doing, because it's measuring the forecastability of the process in an optimal sense. So I think you shouldn't make forecasts, but there is some merit to doing CCM, and it's popular as well. But anyway, it's also measured in there. So anyway, I know this is about brain, but I'm also going to sell you this paper because it compares a number of different methods in kind of a long study format, and it was this recent Nature Communications. So I'm going to call that my last slide, and I'm only a little bit over, sorry.